Every minute, 1 million plastic bottles are purchased worldwide. Most are used once, then discarded forever. Plastic takes 450 years to break down naturally. We have produced more plastic in the last decade than all of human history before it. But in 2016, a bacterium changed everything. Scientists discovered a microbe that eats plastic for breakfast. Hit subscribe because the way we deal with plastic just changed forever. For most of human history, waste was simple. You discarded something, and nature took care of the rest. Food scraps decomposed, wood rotted, fabric dissolved. The planet had billions of years of practice breaking things down. Then, in 1907, a Belgian chemist named Leo Baekeland invented something the planet had never encountered before: Bakelite, the world's first fully synthetic plastic. Durable, cheap, and moldable into almost any shape, industry loved it immediately. Within decades, plastic had replaced glass, metal, and wood across almost every sector of manufacturing and daily life. By 2019, the world was producing 460 million tons of plastic every single year, and that number keeps climbing. But plastic has a dark side nobody fully reckoned with. It is, by design, virtually indestructible in the natural world. A plastic bottle tossed into the ocean today will still be there in the year 2475. It doesn't disappear. It just breaks into smaller and smaller fragments until it becomes something far more dangerous: microplastics. Right now, an estimated 358 trillion microplastic particles are floating on the surface of the world's oceans. Microplastics have been detected in Arctic ice, in the deepest ocean trenches, in the air we breathe, and in human blood. At least 4,000 plastic-associated chemicals are considered hazardous, with links to endocrine disruption, cancer, and developmental damage. Mechanical recycling, melting plastic down and reshaping it, was supposed to solve the problem. It never came close. Only 10% of all plastic ever produced has actually been recycled. The other 90% is still out there. The system was broken from the start, and the planet has been absorbing the consequences ever since we realized it. But buried inside this crisis was a clue, a biological one, and it came from the most unlikely place imaginable. In 2016, researchers at Kyoto University were studying a plastic recycling facility in Japan when they found something extraordinary. A previously unknown bacterium was living in the wastewater, and it was consuming PET plastic as its primary food source. The bacterium was named Ideonella sakaiensis, and what it could do defied everything scientists thought they knew about plastic. It had evolved, entirely on its own, to break PET plastic down into harmless, natural compounds over time. The key was two enzymes the bacterium produced: PETase, which attacks the plastic surface first, and MHETase, which finishes the job, breaking the remaining fragments all the way down to their base molecules. Together, these two enzymes form a biological recycling system that converts solid plastic into reusable chemical building blocks. The outputs, terephthalic acid and ethylene glycol, are the exact same raw materials used to manufacture new PET plastic from scratch. This is what scientists call infinite recycling: the same material looping endlessly without degrading in quality. But wild Ideonella sakaiensis was slow, far too slow to matter at the scale the crisis demanded. So scientists did what scientists do. They took nature's blueprint and engineered something dramatically faster and more powerful. In 2022, a team at the University of Texas used machine learning to design FAST-PETase. FAST-PETase degrades plastic in days rather than centuries and operates at room temperature with no industrial heating required.
Then came TurboPETase, a computationally redesigned variant achieving near-complete depolymerization of post-consumer plastic bottles at industrially relevant scale. And in 2025, researchers discovered GuaPA, the first archaeopetase ever found, deep in ocean sediments. GuaPA can break down PET films within 48 hours, and it originates from an entirely new class of enzyme. To understand what this technology means in practice, you need to meet one company at the frontier, Carbios, a French biotech company that has spent over a decade turning enzyme science into industrial reality. Their technology, called Enzymes, uses an engineered enzyme to depolymerize PET waste entirely in a solvent-free process. The outputs are purified back to virgin-quality terephthalic acid and ethylene glycol, indistinguishable from petrochemical-derived raw materials. That means plastic recycled through Enzymes can become new plastic bottles of identical quality, infinitely. Carbios has already proven this works. Their demonstration plant in Clermont-Ferrand has been operational since 2021. Major fashion brands took notice. On, Patagonia, Puma, Salomon, and PVH, the parent company of Calvin Klein, all signed on. Together, they unveiled the world's first garment made from 100% enzymatically recycled polyester textile waste. Not a prototype, not a concept, a real piece of clothing made from what was once plastic waste. In April 2024, Carbios broke ground on the world's first full-scale industrial enzymatic PET recycling plant in Longlaville, France. The plant will have the capacity to process 50,000 tons of PET waste every single year at full operation. That is enough to recycle approximately 2 billion plastic bottles annually, from waste back to virgin-quality plastic. The plant is expected to be fully operational by 2027, and Carbios is already planning its next facilities globally. In November 2025, Carbios signed an agreement with Wankai, China's fourth-largest PET producer, to deploy in Asia. The target? 1 million tons of enzymatic PET recycling capacity across Asia, a number that redefines the word scale.
The science sounds remarkable in theory, but what does the data actually tell us when we look at the numbers? Start with the enzyme performance itself. Wild Ideonella sakaiensis degrades PET at a rate measured in months and years. FAST-PETase, the machine learning engineered variant from UT Austin, degrades the same material in as little as 24 hours. TurboPETase goes further still, achieving 98% depolymerization of post-consumer PET bottles at high industrial solids loading. That 98% figure matters enormously. Previous industrial enzyme variants plateaued at around 90%. The remaining fraction was considered non-recyclable. TurboPETase doesn't just improve the yield, it does so at industrially relevant scale, meaning real factories, real volumes. Carbios' demonstration plant has processed 2 tons of PET waste per day using their engineered enzyme system since 2021. The monomers recovered achieve purities above 99%, making them directly suitable for repolymerization into virgin-grade plastic. A whole-cell biocatalyst system developed in 2025 achieved complete PET depolymerization at just 30 degrees Celsius with no waste byproducts. Room temperature operation is a critical breakthrough. It means the process requires dramatically less energy than conventional plastic recycling methods. Directed evolution techniques have produced mutant enzyme variants with up to 30 times greater activity than the original wild-type PETase. Enzyme production costs remain the biggest barrier, but solid-state fermentation using agricultural byproducts could reduce those costs by tenfold. PETase enzymes fixed onto graphene oxide sheets or magnetic nanoparticles become significantly more heat-resistant and reusable across multiple processing cycles. And the GuaPA archaeal enzyme found in deep-sea sediments brings an entirely new structural class into the engineering pipeline. Each new discovery expands what is possible. The enzyme toolkit for plastic degradation grows more powerful with every passing year. The trajectory is clear.
What started as a curiosity in a Japanese recycling facility is becoming a global industrial revolution. Enzymatic recycling isn't just a better way to deal with plastic waste. It represents a fundamental shift in how we think about materials. For most of industrial history, we have operated on a take, make, dispose model. Resources extracted, products made, waste discarded. Enzymatic recycling breaks that linear chain entirely. The end of a product's life becomes the beginning of its next one. This matters because the plastic crisis is not slowing down. Global plastic production is projected to triple by the year 2060. Without a genuine circular solution, the amount of plastic entering our oceans will increase to 53 million tons per year by 2030. Enzymatic recycling addresses something mechanical recycling never could: colored plastics, multi-layered packaging, and contaminated textile waste streams. Traditional mechanical recycling requires clean, sorted, single-material plastic. Enzymatic processes are far more tolerant of real-world contaminated waste streams. That flexibility is enormous, because in the real world, most plastic waste arrives contaminated, mixed, and impossible to sort economically. But enzymatic recycling also raises serious questions that scientists, regulators, and ethicists are only beginning to grapple with. The first question is scale. Can enzymatic recycling ever process plastic fast enough to outpace the rate we produce it? Right now, the answer is no. Carbios' first industrial plant won't even be operational until 2027 at the earliest, and even at full capacity, 50,000 tons per year represents a fraction of the hundreds of millions of tons produced annually. The second question is what happens to plastics that aren't PET? PET only targets one specific polymer type. Polyethylene, polypropylene, polystyrene, these make up enormous portions of global plastic waste and remain largely resistant to current enzyme approaches. Dedicated enzyme discovery efforts are underway for these polymers, but the science is years, possibly decades, behind PET development. The third question is economic. Enzyme production remains expensive, and without cost parity, industrial adoption will always lag behind intention. Solid-state fermentation methods using agricultural waste could theoretically cut enzyme production costs by a factor of 10. Theoretically. But theory and industrial deployment are separated by years of engineering, capital investment, regulatory approval, and real-world operational risk. There is also a deeper philosophical risk. If we believe enzymes will clean up our plastic, do we stop reducing production? This is what ethicists call moral hazard, the risk that a technological solution removes the urgency to change the underlying behavior. The United Nations has been pursuing a legally binding global plastics treaty since 2022. Negotiations are ongoing and deeply contested. Without upstream reduction in plastic production, no recycling technology, enzymatic or otherwise, can fully solve what is fundamentally a production problem. And yet, dismissing enzyme recycling because it isn't a complete solution would be a profound mistake. For the billions of tons of plastic already in existence, already in our oceans, our soil, our bodies, we need this. Enzymatic recycling won't save us from ourselves, but it may be the most powerful tool we have to undo the damage already done. We are standing at the beginning of something genuinely unprecedented, a biological answer to one of our greatest industrial mistakes. The enzymes are real. The science is proven. The first industrial plants are being built right now as you watch this. We don't know yet if it will scale fast enough. We don't know if the economics will land in time. What we do know is this. For the first time in history, we have a tool that can undo plastic pollution at the molecular level. The plastic age created a problem nature couldn't solve. Now we're engineering nature itself to fix what we broke. Recycling just got a molecular upgrade. Hit like, share this with someone, and subscribe to SynthCosmos. We cover the science reshaping our world as we know it every single week. We'll see you in the next one.